So we've seen that our model of a flying car with 4 1 square meter fans blowing air down 50 meters per second burned an awful lot of fuel. We're getting through about 10 times more fuel than a normal car driving to Sydney. So does this mean the idea is dead, or is there some way past this? Well, one possibility is that we just ignore the high power consumption. If you went back to 1850, people would have done the same calculation and said that the internal combustion engine, the car, is totally ludicrous, because driving a petrol-driven car from Manchester to London takes vastly more energy than riding a horse from Manchester to London. But luckily back then, vastly more energy was available because of the development of fossil fuels. So the fact that something needs vastly more energy is only a problem if we're going to use the same carbon-producing inefficient energy sources we have now. If someone has portable fusion reactors or matter-antimatter drives or something else like that, then that might make flying cars perfectly feasible. We'll come back later in the course to fundamental limits to energy sources. But if we're stuck with internal combustion engines or something like that, then that huge energy consumption is a problem. So how can we get the energy consumption down? Well, one thing to note is that we're burning energy per unit time in the air. So as you go from Canberra to Sydney, we're burning a certain number of joules per second while we're in the air. So what that means is if we use less seconds, we get to Sydney faster, which we probably like to do anyway. That's going to cut our energy usage, not increase it. If we get there very, very soon, if it only took 30 seconds to get there, the power usage to stay in the air would be very much smaller. So right now, the energy needed to stay in the air is about 2 by 10 to the 9 joules. But the energy needed to overcome drag is about 2 by 10 to the 8 joules. Now if we go faster, this will go down, but because we're going faster, that will go up. And this is proportional to v squared. This is proportional to the time, which is proportional to 1 over v. So if, for example, we double our speed, that'll bring this down by a factor of 2, so that comes out as about, so it's about 5 by 10 to the 8. And this one will go up by a factor of 4, so it'll be about 8 by 10 to the 8. So what you see is that if you go faster, this does drop. And for a while it's probably good. It looks like the optimum speed would be about 200 kilometers an hour. This has dropped, this has increased, but this has dropped by more, so the sum of those is actually lower than the sum to begin with. But when you start going faster still, let's say 500 or 1000 kilometers per hour, this really blows out because it's proportional to v squared, and so the total power is going to go up. So imagine you have a graph of energy used versus velocity, and if you go very slowly, you're going to use infinite amount of energy because it's going to take you months or years to get anywhere, so a huge amount of energy just hovering in the air. And then this energy, this is the energy due to staying in the air, just keeps going down as you go faster. But the energy due to drag goes up as you go faster, and the sum of the two probably has a minimum somewhere, which looks like from these figures is somewhere about 200 kilometers per hour. So that's going to save us a bit, but it's still going to be 5-6 times worse than a ground car. But now maybe it's worth revisiting going higher. When we did the calculation before, it turned out that whether you went high or low didn't make much difference. But now we're in a situation where the drag is going to be really dominant, and so it might be worth flying higher where the air is thinner. That's going to use up energy of climbing, which is about 10 to the 8 joules, but that's pretty small compared to the other two. So in this case, it looks like the optimum solution for a flying car is to go high and go fast. But even if we do that, it's still 5 or 6 times less efficient than a ground car. Maybe that's not a complete killer, but people might be happy to pay that much to avoid traffic. But what else can we do? Well, one possibility would be not to fly the whole way. Bear in mind the energy depends on how long you stay in the air. So you could actually have a car that drives on the ground until you hit the traffic jams of Sydney and only then takes to the air. That could save an enormous amount of power. So that might be feasible, but then you've got the expense of having a car that can both drive on the ground and in the air. It'd be much more mechanically simple if it could do one or the other, not both. But that's a possibility. Another possibility is to change the size of the fans. We assumed, if you remember, there were 4 fans, each 1 square metre. But if you remember, the force was proportional to the mass per unit time times the velocity, whereas the energy, or rather the power, energy per unit time, is proportional to half mass per unit time v squared. Now, because this depends on v to the 1 and that depends on v to the 2, that should give us a clue as to how we can make things better. Remember, here we had a trade-off. We could have a larger mass, which would be equivalent to larger fans, in which case we need a lower speed, or we could have a smaller mass, smaller fans, and a higher speed. That makes no difference. If you double this, you can halve that, but the force is the same, which it has to be to keep the car in the air. But here, this is v squared. So if, for example, we went with half the mass and double the velocity, that's going to keep the force the same. This goes down by a factor of 2, but that goes up by 2 squared force, and the total power will be doubled. So what that means is that the best way to do this is to have a very large mass per unit time and a small velocity. Blow a lot of air down slowly. The force will be the same, but because this velocity will go down by a lot, velocity squared will go down even more, will more than cancel out the increase in the mass. So if you could find some way of moving 10 times more air down at 10 times less speed, your power will be 10 times less. So one option would be, instead of having 1 square metre fans, to have 10 square metre fans. That's starting to look like a rather uncomfortable car, though. Here's that little tiny car in the middle. It's starting to look a bit more like the hot air balloons, in the sense that the fans are much bigger than the car. So that might not be particularly feasible, but maybe we can make the fans a bit bigger, and that would help a lot. Another way would be to blow something heavier down than air. It's not really an option, but there is a device which, a sort of hoverboard, where people stand on a board, and the board is connected to a pipe which goes to a boat underneath. And you're on the water here, and water is pumped up and squirted down. And these things can be very efficient because you're pushing something with a much higher density down the water, and so you actually can have hoverboards like that. The only trouble is you need a water supply or a boat underneath to pump the water up to you, so it's not very feasible for driving to Sydney.